Hey, welcome everyone to the fourth day of this workshop. We have three very exciting talks today on online learning, optimal stopping, and market design. And it's my pleasure to welcome our first speaker, Pierre Alquier from Riken AIP Tokyo. And he has been kind enough to join us on a very odd hour at his place. So without further ado, let's get started with Pierre's.
Okay, well, first, thank you very much for the invitation. I must say that I was very excited by the program of the workshop, and I'm of course it's a bit late here, so I'm not able to attend all the talks live, but definitely I'm looking forward to watching the videos. And sorry that I cannot attend live, but anyway, so this talk is about some regret bounds for online variational inference. It's based on the paper that was published last year with my former PhD student, Badreddin Sharif Abdelatif, who is now a postdoc in stats at Oxford, and MT Khan, who's the leader of the approximate Bayesian inference team at Riken AIP. And I joined this team actually just at the time where we were writing this paper. And actually, I will start by a quick motivation. Actually, when I joined the team at that time, MT was working with many of his um, co-authors on the paper, actually, where they try to scale Bayesian methods to be able to train deep neural networks, as well as the state of the art using non-Bayesian methods. So of course, the point is that if you try to use a Bayesian method, you expect that in addition to point estimate, you get an estimate of the uncertainty of your prediction. And this is what is represented here by the picture on the right. So on the top, you have like an image, and you try to analyze many batches of this image and understand what they contain, if it contains a car, the road. And actually, they estimated a posterior for such for a neural network. And then actually this posterior, if you sample from it, you get an idea of the uncertainty of the prediction. And actually the zones that are highlighted in the picture below corresponds to high uncertainty in the prediction. So the point is that, of course, Bayesian methods, if you look at textbooks on Monte Carlo method, you have very nice sampling algorithm, but these algorithms are like difficult to scale in reasonably high dimension. So for unreasonably large dimension, like the kind of deep neural networks considered in this paper, it's absolutely not feasible. And it's not possible to target the exact posterior. So people target approximations of the posterior. And the question is actually, can we understand these approximations? And is it possible to provide guarantees on the qualities of these approximations? And I would say it's a big question in some sense, because there are approximations of posteriors in many different frameworks. And I should say a word first, maybe about what kind of approximations are used before I actually come to the online setting. I remind just like a few notations in Bayesian statistics and Bayesian machine learning. So you have a prior pi, and given a set of predictors, that f theta, that you would apply on object x, and true labels y, a loss function L, actually you can propose a pseudo posterior of the form x of minus eta times the sum of the loss functions times the prior. Actually, this is not stricto sensu Bayesian inference. This is why I call that generalized Bayesian inference. Well, when the loss function is a log likelihood and eta is equal to 1, this is actually Bayesian inference, but I will allow like things to be a bit more general. Okay, and as I said, so this posterior is not something that you can hope to reach in many problems, because it's like it might be a very complicated object. And the point is that this posterior, it's been known actually for a very long time that it can be rewritten as a minimization problem. It can be rewritten as the argmin of the expectation with respect to p of the sum of the losses plus the Kullback divergence between P and the prior. So if you minimize this with respect to P, over all the possible probability distribution, you will end up with the posterior distribution. And well, this is a very difficult minimization. If you just consider this as a minimization problem, it's over infinite dimensional space. But the point is, this motivated actually the introduction of the kind of approximation that I will study in this talk, that are called variational approximations. And the idea was, well, if this posterior is too complicated, then let's replace it by the minimizer of the same quantity, but on a smaller family. And then actually you say, well, for example, the family would be a set of Gaussian distributions, and then it makes things much easier because instead of approximating on an infinitely dimensional set, you will simply minimize with respect to a finite dimensional set of parameters. Okay. So it appears that there is a well-known theory that I summarize very briefly, but a very well-known theory to study the consistency of Bayesian inference. So does the true Bayesian posterior converges to a kind of Dirac mass at the best possible parameter? And it appears that, well, actually there are many assumptions, but one of the key assumptions is that if you consider the prior pi, then the prior pi of BRN must be not too small, where BRN is a neighborhood of the optimal parameter that I will denote by theta star. So in some sense, it will be the set of the parameter theta that have an excess risk that is not too large with respect to theta star. And if this set has a prior mass under the prior that is not too small, then actually you end up with proof that Bayesian inference is convergent. Okay, so actually another way to understand this assumption is that if you consider the quantity that is minimized here when you're doing variational approximation, and you consider this quantity not for the minimizer P, but for P being the prior restricted on the set B that is on the neighborhood of theta star. And then actually you obtain that this is bounded. Okay. So this assumption that is quite classical to study Bayesian inference has a kind of interpretation in terms of variational inference. And then actually what I was interested in was to try to understand if such a variational approximation, so that is instead of considering the true minimizer, the posterior, I just consider the variational approximation. Is it possible to derive the same kind of consistency results? And very recently, there was a series of papers. I wrote some of them with my co-authors at NSAE, but like many papers appeared recently, showing that actually you can, for the variational approximation, prove exactly the same concentration results that you can prove for the true posterior, but under just a slight modification of this condition that I will call the prior mass condition. So, as I said, the condition can be interpreted as the fact that the expected sum of the losses plus the Kullback is not too far from the optimal. And this being for P being the prior restricted to a neighborhood of the optimal parameter. And actually, what's the main message of all the papers listed in these slides is that actually variational inference will work on the condition that in the variational approximation family, for example, in the set of Gaussian distributions, there is a distribution P that will satisfy the same inequality. Okay, so all this happened in the past few years, months, and the question that I want to solve in this talk is, is it possible to do the same thing for kind of online Bayesian inference? Okay, so I will try to just be more accurate and ask the questions precisely in the next two slides. So first, you know that if you consider the posterior, you can see it as an online update actually, which means that the posterior at time t plus 1, of course, it's given by exponential of minus the sum of the loss function between 1 and t times the prior, but you can also see it as the posterior at time t just multiplied by the new loss that arrives. Okay, so this is why actually in machine learning, this is often referred to as multiplicative rule update instead of generalized Bayesian inference. The point is that if you decide, if you know that in your context, pi t is too difficult to be computed or to be sampled from, and if you decide to use instead a variational approximation, then how can you make sure that this will still work? If you approximate pi t, then you remultiply by x of minus the loss function, so you will have to remake an approximation of the new thing. Are you sure that the losses will not accumulate, the errors will not accumulate? So how actually do you define such a variational approximation in this context was our first question. And the second question is, if you use not the approximation, but the true posterior, then actually you have some regret bounds. And the result that I write here is very classical. It is known, you find it in every textbook, even though most of the time it is cited, actually, it is stated in the finite case, that is in the case where the set of parameters is finite, but like it's the same idea here. So the sum of the expected losses will be bounded by the infimum of the sum of the expected losses plus a reminder term that is given here, and that contains the Kullback divergence between the aggregation distribution Q and the prior pi. Okay, so this is known for the true posterior. And once again, like, is it possible to derive a similar result for variational approximation? So for something that would be computationally feasible. Just a remark, actually, it's something that is not often written in this way, I think, but it's maybe because it's two different communities. So this result, this regret bound is very well known in the world of online learning, I think. Oh, sorry. But then actually it's not very explicit. So you know that, of course, you will choose eta in square root of 1 over square root of t to try to get a square root regret. But still, you also have to compute the KL between Q and pi. And a way actually to do this in full generality is just to invoke the prior mass condition that is usually used in asymptotic Bayesian statistics. So interestingly enough, as the upper bound contains the same term, that is the sum of the expectation of the losses plus the callback, the prior mass condition just say that this term is bounded in some sense. And so, for example, under a prior mass condition with a radius in square root of log t over t, you will end up with a classical regret bound like that. And it appears that in many cases, like when you use Gaussian distribution for priors and posteriors, for example, then you will end up with the prior mass condition being satisfied for this rate, actually. So it means that the assumptions that are made usually in asymptotic Bayesian statistics, if you plug them, I mean, they are satisfied in many set of probability distributions, and if you plug them in this regret bound, then you obtain like the usual order of magnitudes for the regret. Okay, so as I said, two questions. Can we define sequential updates for variational approximation, and can we get such a regret bound? Well, it appears that the results that I mentioned before, the 4 papers here studying this in a non-online setting, in a batch setting, were quite technical. But in the online case, it was all a question of framing everything into the right framework. So just a reminder, even though like, sorry, I should have removed this slide because of course to give a reminder of on your online gradient algorithm and on follow the regularized leader is kind of joke in front of you, like you all know this much better than I do, but still, well, given a set of predictors, then actually, you know that using the online gradient algorithm, you would predict yt by f theta t of xt and update theta t by using the gradient of the loss that you just received immediately by your prediction. The point is that, of course, I remind this, oh, sorry, just for short, actually, I will replace from now L of f theta t, xt, and yt by L t of theta t. So I will just remove the xt and yt as is done usually to save space. The point is that I'm interested here in the interpretation of this algorithm in terms of follow the regularized leader. Okay, so you linearize the loss function, and you can rewrite this as the sum of the linearized losses plus a penalty that is theta minus theta 1, the starting point, over 2 eta. Or alternatively, actually, you can also rewrite it as just the linearized previous loss plus a penalty that says that you don't go too far from just the previous theta t. It's of course like you just know that by differentiating either 1 or 2, you end up immediately with the online gradient update. And the idea is just like here to use the generalized form of this, that is follow the regularized leader, but plugging as a penalization and as the loss what we want to control in online variational inference. That is actually, we have our set of distributions, say for example Gaussian. So, okay, it's too complicated to compute my posterior distribution, so I will approximate it by a Gaussian. So I decided I have this set of Gaussian, and actually I will mimic the definition of the online gradient algorithm, but by changing the penalty. And in order to mimic what is done in variational inference, I will either define mu t plus 1 as the minimizer of the linearized expectation of the losses, plus the callback between q mu and the prior. Or I could, if I mimic the second expression for the online gradient, I could minimize the gradient of the expected losses I just received at time t, plus the callback divergence between q mu and q mu t. Actually, just a remark, bad luck in online gradient algorithm 1 and 2 are equivalent. In the Bayesian or pseudo-Bayesian framework, they are no longer equivalent. So the first proposition, mu t plus 1, and the second one will not give exactly the same algorithm. Still, both seem natural, actually, so we wanted to study both. And once again, I think that the difficulty here was mostly to cast the algorithm that were already quite popular in practice into the right framework to study them. Because once you have this formula, you know that actually mu t plus 1 is an application of follow the regularized leader that will lead to a regret bound if you have the correct assumptions. And I will state results later. But first, just an example. When you use a Gaussian approximation, we did the computation, and indeed it's possible. It's possible to find like a kind of gradient type update for the two versions. So by the way, I forgot to say that the first version we decided to call that SVA for sequential variational approximation, and the second one SVB for streaming variational base. So SVA, we have actually just a gradient update for M. And we have an update that is slightly more complicated for the variance sigma. So there is a function h that is given just below and that we apply coordinate-wise. For SVB, it's actually quite interesting, the behavior of the algorithm, because in this case, we update the mean and the variance, but what is interesting is that the update of the mean is actually a gradient step, but the step is proportional to the variance. So in some sense, even though our result will not show this, we can expect some kind of adaptation from this algorithm. Anyway, so as I said, the question next was to try to provide a regret bound for this algorithm. And well, if you make the adequate assumptions, then actually this is just follow the regularized leader with a convex loss and strongly convex penalty, so you have a regret bound. So actually, if you assume this, so if you assume that the loss is convex and L Lipschitz, and if you assume that the callback is alpha strongly convex, then you have the usual regret bound for this procedure. And what is interesting is that it really looks like what you would have for the exact base procedure. So the classical regret bound that was provided before. That is not this one proven as a special instance of follow the regularized leader, but rather proven with evening inequality and the Donsker-Varadhan variational formula. So you obtain something that has the same form. And as a consequence, actually, it means that if you do, once again, the kind of prior mass condition, then you will end up with a regret bound that have the usual order of magnitude. Okay, the point is that maybe it's a bit just, of course, easy to say, let's assume that everything is as it should, that is that the loss is convex, the expected loss is convex, that the expected loss is Lipschitz, and that the Kullback is strongly convex. The point is that we must check that in practice, and the good news is that there are results saying that it holds in general. So if the loss is Lipschitz and convex, then actually the expected loss in the case of any location scale model will be Lipschitz and convex as well. Sorry, excuse me, I'm losing my voice. Sorry. So for the Lipschitz claim, actually it's almost trivial. It just takes 2 or 3 lines to write it. For the convexity claim, if you choose the Gaussian family, it's okay. But if you want to choose a more general location scale family for the approximation, like maybe student or anything else, then it becomes quite complicated. And there is a very nice paper by Justin Domke, actually, that was published just in the past few months, where actually he proves these results. Like almost any location scale family, you will have like the expectation will preserve Lipschitz and convexity. So it's quite nice. Regarding the Kullback, it appears that when you deal with the most classical example, that is a Gaussian, then in this case, on the condition that you upper bound the variance, so that is that you constrain the variance not to go above a given threshold, then you will have the strong convexity assumption. So actually you have this regret bound will hold in quite a natural setting. Okay, in a second time, we performed the analysis for SVB. So I remind you maybe the difference just once again. So SVA is when we use the Kullback divergence with respect to the prior, and in SVB, we use the Kullback divergence with respect to the posterior at the previous time step. And in this case, it was just a bit more complicated in the sense that we are not able to provide a general analysis. If you use Gaussian approximations, then more or less it becomes quite similar to what is done when you don't have actually any Bayesian interpretation. Just when you do a gradient descent, you just have to take care of a few extra terms. And in this case, we were able to recover the usual rate, that is in the convex and Lipschitz case, the square root of t regret, and in the strongly convex case, log t regret. Really sorry, I don't know what's happening to my voice. It's quite difficult to talk. But this holds only for Gaussian approximations. So we don't have a general analysis for the second algorithm, only for the first one. I'll just take 1 more minute to talk to you about the results of the numerical experiments that we performed. We compared many algorithms, including our SVA and SVB. OGA is the ordinary online gradient algorithm. So you know it. It's in yellow here. So you see that here SVA is in blue and SVB is in purple. OGA-EL, I will not talk about that for now, but there is this NGVI, mysterious for now, but I will give a word on it later. That you can see here that this mysterious NGVI is better than everything else. Actually, gradient here is the worst one, and then SVA slightly better, SVB really better, and NGVI is the best. And we hoped that we would identify a pattern. It's not the case, actually. So here is another example of classification on another data set. And here you can see that actually the Bayesian methods, the Bayesian methods SVA and SVB are blue and purple. They are convergent, but they are not the best these times, and the online gradient algorithm is better. Still, this green thing here is much better. And in all the simulations we did, like this is the, we did like many data sets, and always what happened was that all the methods work, but there is no clear hierarchy between them, apart from this NGVI in green actually is almost always the best method. NGVI, by the way, I should say, is the algorithm that was at the basis of the idea used in this paper, in the deep learning, Bayesian deep learning paper. So it was the one that we wanted to study initially. The point is that when I come back to my final slide, actually, there is a short explanation here on NGVI, and it is based actually on the same idea. That's a kind of follow the regularized leader where the penalty is a callback. But the point is that it does not use the same parameterization that we used. Okay, so here I talked briefly like about this mean and scale parameterization. It does not use the mean and scale parameterization. It uses a natural parameterization in the exponential family, which is very nice because it makes many calculations quite simple. But on the other hand, it destroys the convexity of the loss and of the callback. So for this reason, this algorithm that works very well in practice is not in the framework of our theoretical results. And that's one of the open questions actually. Important to me is to be able to extend the analysis to this algorithm. Still, we were quite happy to have these results because up to our knowledge, it was the first time that there were some theoretical results on the validity of online variational inference. And there are a few other questions, including like the second one. I think it's quite important because in this case, like, as I said, Bayes is usually motivated by uncertainty quantification, but still the regret bounds basically just give result on prediction and not on uncertainty quantification. So it would also be nice to check if actually these methods provide a reliable uncertainty quantification. This is not stated by the results yet, so there is still some work to be done. Thank you for your attention, and sorry for losing my voice. I hope that you could understand me still.
Thanks, Pierre. Gergie has a question. Gergie, do you want to ask?
Yeah. Thank you, Pete. This is very interesting work, and I guess it's not easy to speak at 1 a.m. So my question is, so like, do you assume that your variational class is convex here, or can you explain where exactly the convexity is happening in these optimization problems?
Okay. So actually, you're right. It's something quite important actually, because if you want to, it's possible, for example, it's possible to derive this regret bound here by working on. I'm sorry, there is some kind of echo, so I cannot hear myself. I don't know if. Okay. Yes, here the result given here can be proven actually as a kind of follow the regularized leader. But then in this case, you have to work on the set of all probability distributions, which can be quite large. In what we do here, actually, the idea, in some sense, was just to avoid working in the set of probability distributions and just to work with parameters. So, for example, you take Gaussian family, and the optimization is no longer on the set of probability distribution, it's just on the set of mean and on the set of variances. So the vector M and the covariance matrix sigma. So actually, in this case, the parametric set that you try to optimize in is convex. If you try to keep the first approach, and if you want to come back to this proof, you will have problems because in the set of probability distributions, the set of Gaussian distribution is not a convex subset. So actually, the idea was just to transfer all the work on the space of parameters rather than on the space of probability distributions. I hope this answers your question.
Yes, it definitely does. And I guess this was really the challenge that you had to face when trying to analyze SVB, right? Because there you have these sequential projections back to the space, and that really needs convexity for like mirror descent algorithms. Yeah, okay, at least that's my guess in this answer, but it's very helpful. Your info, thank you.
So do you need convexity of the set to prove convexity of the loss function? I don't see why. Like, aren't you using the fact that it's an infimum over certain set to prove convexity of the loss function?
Sorry, I missed the beginning of the question. I'm sorry, I did not hear the beginning.
So do you need convexity of the set of distributions to prove convexity of the loss function? Or is it just for like efficiency of
No.
of the
told me that.
fine?
So I would just okay. If you come back to our results, actually, you just have a loss function L. You compute the expectation of L with respect to a probability distribution that is parameterized by mu. Say, for example, a Gaussian with mean mu, and you just need this to be convex with respect to the parameter mu.
And sorry, the strong convexity assumption is on what then? The loss function with respect to theta, or this expected loss under Q?
I mean, in this result here that is stated here, you have convexity on L and strong convexity on the Kullback between Q mu and pi.
Right, but I thought that's always strongly convex, at least in terms of the one norm.
It's
Well, I figured that the KL divergence is always strongly convex with respect to the one norm. Oh, what? Oh, you mean like with respect to mu?
Exactly.
Oh, yes. I see. Very tricky.
Yes. I mean, of course, like if you work in the world of probability distributions,
right,
then yes, it is always, but you're no longer working on a convex set, because
right.
if you have two Gaussian distributions, then just the linear combination of the two Gaussian is no longer a Gaussian.
Right.
So here, the point is, it's frustrating in some sense. We cannot work with the natural object. We have to work with a parameter. And when you work with the parameter, suddenly you can have strange things that happen, and you can have Kullback that is no longer a convex function sometimes of the parameter. It's the case, for example, with the parameterization that is taken, what I mentioned in the last slide, actually. MTCAN, he has this non-convex parameterization, which surprisingly works very well, but we're not able to prove why.
All right, thank you. That's very illuminating. Thanks very much for clarifying that.
So one more question I had was, since you are going to not be part of the discussion, I'm extending this a little bit. Sorry, David, to delay your talk a little bit. I just wanted to have your opinion on, since you're using this generalized Bayesian inference and not using log likelihood in the which would come out if you did the regular variational inference. Is scale divergence still a natural distance measure to use then?
Okay,
it kind of comes out naturally if you in variational inference with log likelihood, but maybe here, since the loss function is not really like likelihood.
So you mean that you would say, for example, here, why do I use as a penalty the Kullback library rather than something else?
So, right.
Actually, I think this is a very good question. Thank you for giving me the opportunity to advertise for a preprint that I just posted on the archive a few weeks ago. So I was interested in this question, like, should I take the KL or should I take something else? It appears that if you replace KL by something else, you obtain something that is sometimes interesting, because you can slightly change the hypothesis on your algorithm. So, for example, even when you don't have any variational approximation, when you work with the full any probability distribution Q setting, actually, if you replace the KL by another divergence, sometimes you can get rid of the assumption that the loss is bounded here, L. But the price to pay is that usually for all the other divergences I tried, you have a worse regret bound, which means that actually you don't have square root of T, but you can have something that is bigger. So apart from like removing some hypotheses that can be useful, of course, but apart from that, I'm not convinced yet, actually. So I've seen, actually, I didn't know that, but since I posted this new preprint, I realized that many people actually tried this idea to replace the KL by something else. And there are very elegant results, but the application in practice, maybe it will be very helpful, maybe not, but I don't know yet, actually. So that's.
Thank you. Yeah, thank you. Unless there are any pressing questions, I think we should move on to the next talk. David, can you